Hello everyone. This tutorial is about the simulation of tube-in-tube helical coil heat exchanger. The double tube heat exchanger is made of copper in which hot and cold water flow in opposite directions. The cold water flows in outer tube while hot water flows in inner tube. The operating condition is at standard pressure 101,300 Pascal for all, whereas the inlet temperatures are 285 Kelvin and 350 Kelvin for cold and hot fluid respectively. The RNG K epsilon viscous model with enhanced wall treatment is used to model the flow using ANSYS Fluent 2019 R2. The top side of the double tube heat exchanger shows cold water inlet and hot water outlet. The outer diameter is 38 mm with 1 mm thickness, while the inner diameter is 15 mm with the same thickness of copper tube. The bottom side shows cold water outlet and hot water inlet. The geometry will have four concentric circles for inlet, outlet and the pipe interfaces. I will draw a line, then circles and use sweep tool to form the helical coil with two turns. So open ANSYS workbench program and select Fluent package from analysis. However, separate components can also be selected from system component list. Right mouse click on geometry and select new design modular geometry. So first of all, according to the dimension of geometry, set unit to millimeter and select a plane which is XZ plane in this case, and right mouse click to look at. Now draw a line, navigate to sketching toolboxes and under draw select the line. Now from the origin make a horizontal line, keeping it on the axis with unspecific dimension. Now click dimensions and select general to specify its dimension. Click the points and set the dimension to 150 mm. Now select another sketch from commonly used options and go to draw. Select a circle to draw the inlet circle, selecting the axis normal to the axis of the line. Draw a circle of unspecified dimension and then set the dimension of the circle to 15 mm. Also select the center of this circle and set the dimension of the length from the origin and set the length to 100 mm. Now we have to draw three more circles for the interface of the pipe, for the outlet domain and also the outer pipe thickness. So select a new sketch and draw a circle, actually two circles that will be showing the thickness of the pipe. After that, add new sketch and other two circles. Finally, add another sketch for two more circles. Now go to dimensions and select general for setting the diameters. So for the first circle, the dimensions are diameter 15 mm and the vertical distance of 100 millimeter. For sketch 3 circles, set the dimension of the inner circle to 15 and outer to 17. For sketch 4, 17 and then 38. That shows the outer domain of the pipe. And for sketch 5, inner diameter 38, outer diameter 40 millimeter. So this represents the thickness of the pipe. So now we can use the sweep to draw the helical pipe. So click the sweep icon and click the first sketch, which is the inner domain for the profile, and this line is used as a reference. It has nothing to do with the geometry, it just provides the path. So click the line for path, set operation to add frozen, and twist specification to turns, setting the number of turns to 2. Then click generate. So we will have a helical coil with 2 turns. Similarly, select another sweep, now selecting the other sketches for the profile. For the interface and path as the reference line. Add frozen and set twist specification to turns and number of turns to 2. Another sweep, selecting sketch 4 now and path as sketch 1. Add frozen, turns to 2. That for the outer domain of the pipe. Another sweep, select sketch 5 and sketch 1 as the path. Repeat the process. So here we have the helical coil geometry. Now we have to extrude the inlets and outlets, and we will use the extrude command by selecting the faces. So first select the top face with this face selection tool. And then use the extrude tool with add frozen. And direction of the vector normal to the face. With depth 200 millimeter. Click generate to get the extruded part. Now repeat the process for the bottom of the coil. So select the faces. Click extrude. Select the direction vector normal to the face. And click generate. So now we have many bodies that are of swept and extruded. But remember, we don't have to add the material. We can change from here. So now we can use the Boolean command to merge the extruded tools as well as the coil. So now select the face and with 3 bodies, go to create, click Boolean and unite them. Now hide this body and again select the extruded parts and the helical coil and repeat the process. Similarly for the inner interface, boolean, unite, apply, and for the inner domain. Now navigate to the bodies and right mouse click on all of them to form a new part. So our geometry is completed. Now we have to name the faces and the bodies of this geometry so that we can set the boundary conditions. We can also perform the naming in meshing program. So click the face tool and select the top face, right mouse click, name selection and name it as hot inlet. Also selecting the outer domain, name it as cold inlet. My bad, this face is actually hot outlet and at the bottom the hot fluid is entered, so we can change the name as well. So at the bottom this is hot inlet and this is cold outlet. Now select the four faces of the interface. From the bottom and from the top as well. Holding the control button. That's total four faces and name them side walls. Now select the face of the outer pipe and name it as outer pipe, outer wall. Now hide this geometry and name it as cold fluid outer pipe interface. Now hide this as well. Select the faces and name it as cold fluid inner pipe interface. Now hide this as well. Click the faces and name it as hot fluid pipe wall interface. So we have cold outlet, cold inlet, hot inlet, cold outlet, side walls and the interface and the outer wall. So now Select the body selection tool and name it as hot fluid domain. Now show this body and select this body and name it as inner tube. Show this body and select this and name it as cold fluid domain. Now show this body and name it as outer tube. Now close the design modeler and return to the workbench program. Save the program, make a new folder and setting the file name. You will see a green tick next to the geometry within your project. Now start meshing. In the meshing program, click Generate to get the rough mesh. After meshing is performed, click Mesh and set the display style to skewness. Here we can check the skewness of the mesh, which is near to 1. That means the skewness is very large. Almost all the area is skewed. So we will try to generate a mesh with less skewness. In order to do that, right mouse click and insert sizing. Here we can size the edge of the front face and the back face. Take the edge. Also, at the back, hold Control button and click the edge at the back of the coil. So there will be total 8 edges selected for the geometry. Now set the type to number of divisions and set number of divisions to 60 or maybe 30. Set the behavior to hard and then generate mesh. So now check the mesh skewness again. Almost skewness is 60 to 70%. So we have to perform edge sizing again. Let's do the edge sizing separately for inner tube and outer tube. So select the inner tube first. With 30 number of divisions and then do the edge sizing for outer tube. Set the number of divisions to 50 and behavior to hard. Then generate the mesh again. Check mesh skewness again. So now most of the area has this green yellow color, which means the skewness is decreased. Around 40 to 50% skewness is present. So that's fine. Our equation can be solved in Fluent program. So close the meshing program and then update the mesh. There will be a green tick next to the mesh. Now it's time to set the model and the boundary conditions. So double click setup, double precision, okay. So check gravity and set the gravitational acceleration to minus 9.81 in y value. Then double click models and select energy equation. Then double click viscous model and select K epsilon 2 equation. Click RNG model and then check enhanced wall treatment. So this RNG model, which is renormalized group model, it damps out the time dependent velocity fluctuations, and the enhanced wall treatment is for the near wall to have values near the wall and make it sensitive. After that, set the materials. Select Fluent database and set fluid as water liquid. Copy, close, change, close, and solid to copper. Because the tubes are made of copper and the water is flowing inside the tubes. Now double click cell zone conditions and then select the domain, material, water liquid. Similarly, for the hot fluid, set the material to water, and for the tubes, set the material to copper. Now double click boundary conditions. There are many boundary conditions to be set. So double click cold inlet and set the velocity magnitude to 1 and temperature to 285 Kelvin. Set outlets to pressure outlets. Hot inlet with velocity magnitude to 0.7 meter per second and temperature to 350 Kelvin. Now for all the wall, set thermal conditions to coupled. Also set the material to copper. Retain all the default settings for interior, and set the outer pipe thermal condition via system coupling as well as the material name to copper. So all done. Now double click methods in solution list and select scheme simple with the gradient of spatial discretization as green Gauss cell based with all the discretization schemes to second order. Now double click monitors and set the residuals to 1 exponent minus 6 for all the equations. And double click initialization, select standard initialization and compute from all zones. Retain default settings for all the parameters and then click initialize. Now double click run calculation and set number of iterations to 1000 and then click calculate. Now I will pause my recording here and let the solution to run. So the solution is converged at 390 iterations. Now if I want to obtain average temperature values at inlet and outlet, click reports and then double click surface integrals. Set report type to facet average. This will give the average value at the face. So check total pressure and click inlet and outlet. First I will check the total pressure and then temperature and then the velocity values. Click compute. So there are the average values of total pressure at the face of inlet and outlet of cold fluid and hot fluid. Similarly, select temperature and select inlet and outlet and then compute. So the average of facet values for static temperature in Kelvin are visible in console box. And then for velocity, click compute and we will get the velocity magnitude for inlet and outlet. Now close Fluent program and open CFD post for results. So in order to get the temperature field distribution, click contour and then select the interface. For the inner pipe, click hot fluid pipe interface shadow, select temperature and number of contours 200. So for the local variation, click range to local and select apply. So here is the temperature variation in the inner pipe. For outer pipe, select the location as cold fluid outer pipe interface shadow. So here it is, the outer pipe temperature variation. Similarly, if we want the inlet and outlet temperature variation on the face, select the locations holding control button, control inlet, control outlet, hot inlet, hot outlet and press OK. Click apply and you will see the temperature variation in inlet and outlet. So this one is the bottom face and this one is the top face. You will see that how the temperature is changing for the hot fluid when it enters the pipe. Now if we want to see what is the variation if we section the coil. So for sectioning, select plane and set the plane to ZX with slice plane type and click apply. Go back to contour, or you can generate another contour, but here we will set the location to plane 1, click apply, and here it is, the temperature variation when you section the coil. We can modify the legend by clicking default legend view and select appearance, change the size, change precision to fixed, and click apply to get the fixed values instead of scientific. To save the plot, we can right mouse click and save picture and select the directory. Select white background. We can change the width and height to set the resolution. And click save. So by this way we can generate quality plots. So thank you for listening. In this tutorial, we get to know how to create the geometry using extrude and sweep tool. Also, we checked the meshing by understanding the skewness and we tried to minimize it by setting the edge size. Also, we described the material and cell zone conditions in ANSYS Fluent. Then we used RNG K epsilon turbulence model with enhanced wall treatment. Also, we found average values on the face of the geometry for temperature, velocity and pressure, then the contour plots in CFD post.